Hi, I'm Antonio Sala, and in this video we are going to discuss how to code in Matlab the simulation of a number of bodies interacting with gravitational forces. In other videos we'll see some examples, escape velocity, elliptical orbits and whatever. In here we'll concentrate on how to code and animate the simulation you're watching now. So let's go with the code. And the basic idea of any Matlab simulation in which we use command line, scripts, not Simulink, is that everything goes around how to call a suitable numerical integrator. So this is the numerical integrator ode113, which I solved because Matlab's documentation tells me that this one is better with stringent error tolerances, and ode113 excels in orbital dynamics so well. If Matlab guys say that, they know more about orbital mechanics than I do, so I'll respect their will. And in fact, I will set stringent tolerances because if you simulate orbital mechanics, that must be conservative. With not so good tolerances, then you may see some drifting, so that energy or momentum doesn't seem to be conserved. So in order to at least conserve energy and momentum within sensible tolerances for a long time, we need stringent tolerance options. So I will set these ones. And the goal for numerical integration is, of course, simulating from a given initial state the time evolution of the state via state equation that tells me the derivatives of this state. So in our code, the state will be formed by the x position and y position of all the bodies involved in the movement and the x velocity and y velocity. So for instance, in this 5-body simulation, my state vector will be of size 20. In here, I will use some temporary arrays storing positions and velocities, which will be encoded as 2 times n matrices, so columns refer to each of the objects. Body 1, 2, 3, 4, and 5, they have a position x, a position y, and same for speeds in row 1, x, and row 2, y. So depending on whether we address rows, such as in this case, we are getting the 5 x positions and the 5 y positions, same for speeds. And if we address columns, later on when computing gravitational force, then we will obtain a column vector with the xy position of a given body. So this is how we organize our data. This is the state, and I need to decide a given simulation time, and I will call the numerical integration routine with the physics, the most important piece of the code here. We're going to delve in a minute. A function that computes the derivatives of a given state of the system at instant lowercase t. So then uppercase t will return the sampling instance with tolerance-dependent integration step, and in the solution it will give me an array of all the state variables, in this case 20, at the given time instance. I give times to simulate, initial state, and tolerance options to carry out the simulation. So this is basically the skeleton of any simulation: tolerances, initial state, and which integrator I use, and then the physics is in here in the highlighted segment of code. So let us delve into the details. This is the core of our simulation. But as this is a mechanical system, well, states are positions and velocities. So basically, if I start by looking at the last line, the derivatives of the position will be velocities, and the derivatives of velocities will be accelerations. And I will have somehow the accelerations in the x-coordinate and the accelerations in the y-coordinate separated. So good, let's now delve into the prior lines. If I have 5 bodies, I have 5 positions and 5 speeds, each of them with x, y coordinates. So I have 20 state variables. So the number of bodies is the length of state variables divided by 20. And the 2 times n vector of positions, the first row, positions in x coordinate, will be the first capital N elements of the state vector. And the next capital N elements of this state vector will be the y position. So I build that array like that. And the velocities will be the remaining elements of the state vector with this size. And I will not reshape it like this because, well, as the gravity acceleration depends only on positions, there is no friction that might depend on velocities, so I need only the positions. Then I will just keep these 2n velocities, and I will say that those will be the derivatives of the corresponding positions. But acceleration will return for me also a 2 times n acceleration vector, which again I will assume it is arranged in this way. So that's why I take this row and transpose it to put it here, and likewise I do that with the y coordinate. So let us go to the core of what is gravity acceleration computation. But well, as gravity depends on distances, then I have an auxiliary function I called pairwise separation, computing, well, the vector of pairwise separation, in vector units, the cyan vector separating body I from body j, and dividing the cyan vector by its modulus, which is the distance. This is the modulus of the separation vector. So then later on, I will be able to build a unit vector in the force direction. But in here, in this auxiliary function, I just compute the vector separating one body from another and the scalar distance for all possible pairs of bodies. But, well, if I compute distance from body 1 to body 8, then I don't need to compute from body 8 to body 1 because it's just the same, the vector will be the opposite sign and the distance will be the same. So I will skip that computations. So that's why this second loop only discusses the upper diagonal, let's say, because also the distance and the force from body I to I will be just 0. So good, with this auxiliary function, I now go to the core gravity acceleration computation by first calling my pairwise separation stuff to compute all the vectors and scalar separations, and then for any pair of bodies y and j, again no need of all of them because of symmetry, then the modulus of the gravitational force is just Newton's formula, gravitational constant, which is a global variable I defined elsewhere, times the product of masses divided by the square of the distance between bodies I and j. Then, dividing the vector separation by the distance, I get the unit vector in the direction that joins the two bodies, so it will be this kind of small red arrow in here. And then if I multiply that vector times the magnitude of the gravitational force, I will obtain the gravitational force vector pointing in the direction of the other body attracting the body I am considering. So that is what I am doing in this line. I multiply the unit direction vector times the modulus of the gravitational force. And by symmetry, the other body will be attracted with the same force but in opposite direction towards the first body. So that's why I put ij with no minus sign and ji. I just add the minus sign. And I don't execute all n² combinations in the loop. And well, I add the idea that the force of any of the bodies with himself is just 0. Well, once I have the force vector, I just need to add up all of them to obtain the resulting force and divide by mass to get acceleration, and this is done in this fragment of code. Instead of adding the force and then dividing by mass at the end, I will add to the acceleration each pairwise force divided by the mass of the object I am considering. And in here I am considering all n² possible pairs. So I mean body 1, I am computing the acceleration with 1, 1, which is 0. This AC matrix, acceleration matrix, was initialized to 0. And then 1, 2, 1, 3, 1, 4, whatever. And for the second body, well, I compute the force with body 1 divided by the mass of the second body, 2, 2, which is 0, 2, 3, whatever, so I get n² combinations because forces are symmetric, but accelerations are not symmetric because, the masses of body I and body j may be different, so I am dividing by a different factor. So with this last nested loop, I do compute the acceleration vector xy in column that I put that column in column I corresponding to the body. I am computing this element of the overall acceleration AC matrix in which I store everything. So once I finish this, I can use its output to form the derivative of the for n-dimensional state for the numerical integrator, and that's it. With this line, I have carried out the simulation. So the rest is just animation and plotting. We will briefly outline how to do it, but it's just a couple of plot commands. You may skip if you are just interested in the physics and not in the detail of Matlab animations. But okay, if you are interested, let's go. In this line I recover from the 4 times capital N states. These are the x position, these are the y position, the second group of n numbers, and this is the minimum maximum of x position and minimum maximum of y position, just to draw the figure x's. And then animation is, well, we have a lot of frames. Each element of capital T from the ODE solver is a frame, and I have capital N bodies, so at each frame I draw all the bodies. Well, the body will be just a circle, this line, in which I put the x position at a given frame of a given body, and the y position I draw a circle with a given line width and marker size I defined in the start of the simulation. I hold on because I am drawing a lot of bodies, and then I also will draw a line, not a circle, with somehow the past positions, so that my moving bodies leave a trail, little wake behind them so I can better assert and understand how they are moving. Instead of just a circle, I see part of the past trajectory, and in this case it's just frame divided by 2, the start of the trailing trajectory I am going to plot, and that's it. I do that for each of the frames, draw now, and repeat, and this is how I get the animation. So any particular example starts with given initial positions and velocity and marker sizes for the animation, and they'll end up drawing these trajectories. So we conclude here. In this video we have seen the details on the simulation code in Matlab for the n-body problem with gravity interaction. This may be not the fastest or more accurate, but this is a Matlab tutorial, and we also saw the animation with these circles and the color line describing the past trajectory. In subsequent videos we'll analyze some more examples and the concept of escape velocity, potential energy, and the like. For the moment being, we end here. Thanks for watching.